Hello, my name is Walker Gallman. Today I will be covering my lab report for Lab 2 in Physics 2211 on the topic of the motion of a falling object. To introduce this lab, the purpose is to observe the motion of an object falling from rest and to depict and interpret how gravity and drag affect the object dropped from rest. A few assumptions include that gravity and drag are the only forces acting on the system. The initial velocity of the paper ball is 0 meters per second, and the initial position of the paper ball is at 0.0873 meters in the y-axis. A few fundamental physical principles include Newton's second law of motion. Newton's second law, the momentum principle, states that the rate of change in momentum is directly proportional to the net force exerted on a system. In other words, the net force is equal to the product of the mass of a system and its velocity. From Newton's second law, we can derive it to achieve the velocity update formula, which is used to find the velocity of an object after a time period. Related to the velocity update formula is the position update formula, which is used to find the new position of an object after a time period has passed. The position and velocity update formulas allow for us to predict both the future position of a system and the future velocity of a system. Other important formulas used in this lab are the universal gravitational formula, which can be simplified to the gravitation force close to Earth as a constant 9.8 meters per second squared. Also, the formula for the force due to drag is used in one of the computational models, Model 2. This experiment utilized two online programs, GlowScript and Tracker, to allow for a comparison between a physical observation of motion and two computational simulated models, with GlowScript being an online coding platform that created the computational models, and Tracker being a software that tracks the motion of an object using a recorded video. A preview of the main results of the lab included the observed physical motion closely resembles the simulated motion of the object, which supports the fundamental physical principles previously mentioned. For the experimental setup, the system is defined as a crumpled paper ball, and the surroundings include the forces due to gravity and drag. For the initial conditions of the experiment, the ball specifications remain unchanged, having a mass of 0.0045 kilograms and a 0.076 meter diameter. The initial position of the ball was at 0.0873 meters in the y-axis, and the initial velocity of the system is assumed to be 0 meters per second. For the experimental process, the experiment began with taking a video capturing the physical motion or movement of the ball dropped from a height of roughly 3 feet. After this, the video was uploaded onto the Tracker software, where the motion was tracked and its relevant information, position at variable times, was documented. Next, two computational models were developed using the GlowScript platform to simulate the movement of an identical system under the influence of only gravity in one model and under the influence of gravity and drag in the other model. After the data was collected from the simulation, the three datasets were overlaid to compare general trends. Here's a video of the Tracker software. Here is a graph of the data gathered from the Tracker software to estimate the motion of the ball in the real world. For the first computational model, where the ball is subject to the force of gravity alone, the initial conditions were outlined with the ball mass and the initial position vector. Additionally, the force of gravity was used in line 71, right here, with the formula minus mg, as well as the velocity update formula is used in line 75, and the position update formula is used in line 77. On the right is the experimental data from Model 1, and it follows the same exponential-like regression over the time interval. For Model 2, where the ball is subject to both gravity and drag, the same processes are mirrored from Model 1, except that the drag coefficient is now identified in line 56. The gravitational force and drag force formulas are now used in line 70, and the velocity and position update formulas are used in the same lines, line 74 and 76. All three graphs follow the same general trend, matching that of an exponential regression, but the data from the Tracker deviated significantly towards the end of the experimental frame, likely due to tracking error. Potential sources of error in this experiment range from human errors being an initial applied force that led to an initial velocity rather than no velocity, or programming errors such as coding errors or inaccurate tracking inputs and calibration settings, and surrounding errors such as air disturbance due to the air conditioner being on in the room. Now, moving on to the extension questions. Examine the velocity versus time predicted by your models with and without drag. Which models predict a terminal velocity discussed briefly? Terminal velocity occurs when the force of gravity pointing downwards is equaled by the force of drag pointing upwards. This indicates that an object traveling at its terminal velocity experiences a net zero force. Drag is a critical component for terminal velocity, so Model 2 best predicts terminal velocities. For the question, imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? If the object was thrown downwards, the end velocity would remain the same. Only drag and the force of gravity are important, and the initial velocity would eventually level out. Therefore, throwing an object downward would cause it to slow down until it eventually reaches its terminal velocity as predicted in Model 2 with both drag and gravity. Thank you.